All right, thanks for being here. What I'd like to discuss today are some very important considerations that we need to make regarding what chemicals and materials are used to support the important transition to clean energy technology and decarbonization. So whenever we are considering sustainability, it is important to think very comprehensively, although this can be challenging, and to understand the important feedbacks, interactions, and impacts of the effects of human systems, human activities on environmental systems. The planetary boundaries concept is widely used to help us do this. It establishes 9 different safe operating limits for environmental systems, and if you are exceeding or approaching exceedance of those safe operating limits, it means human systems are starting to seriously threaten the sustainability of the planet's environmental systems to continue to support ecosystems that support all life, at least as we know it on the planet today. So I've arranged the 7 planetary boundaries, which in 2015 had an established safe operating limit in order of which ones we are most exceeding. You might notice that while climate change is certainly there, it is certainly important, it is not actually top of the list. The planetary boundaries that we are in greatest exceedance of relate to excess nutrient runoff from agriculture and loss of biodiversity due to habitat destruction and species extinction. There is one good story here. We have improved on one, which is stratospheric ozone, and this is a great example of the importance and value of effective policy. So the Montreal Protocol, which regulated carbofluorocarbon refrigerants out, is the main driver behind that improvement. There's also 2 planetary boundaries that at this time, a safe operating limit was not established for. Atmospheric aerosols, which is my main area of research, but we're not going to talk about them today. And novel entities, which is another way of talking about synthetic chemicals and materials. So the planetary boundaries concept has evolved since it was first introduced in 2009. And just last year, it was updated. And now the safe operating limits for the 2 remaining boundaries were established. And you might notice that climate change is there, and it has grown in exceedance beyond its safe operating limit. But now there is a safe operating limit established for novel entities, the synthetic chemicals, and this is actually the planetary boundary that we are in the greatest exceedance of, and that exceedance is growing the most rapidly. And so that's what I want to focus on today. There's a lot of understandable focus on climate change and decarbonization, but along with that, we also need to consider, well, what chemicals are we using, because we don't want to continue to exceed this other important planetary boundary, because this planetary boundary comes from the toxic effects that harmful chemicals, even though they have useful properties in their intended use, when they release into the environment and then get into organisms, they have toxic effects, and that's what we need to consider. So we're going to focus on the forever chemicals, or PFAS. These are the polyfluorinated alkyl substances. The main takeaway from these chemical structures is all the carbon-fluorine bonds. This is what gives them their unique and valuable properties. This is what makes them polyfluorinated, but it also comes along with some problems. So there's a lot of useful properties of these polyfluorinated molecules, which is why they're so widely used. We could find them all over the place in this room, including in my cell phone, which I touch hundreds of times a day. But focusing on the energy space, they are used in fuel cells, solar panels, lithium-ion batteries, and semiconductors to make microchips. And you can see here one first example, and we're going to dive into this idea that we need to use chemicals like PFAS in order to make materials that have good properties, such as semiconductors. And we're going to take that apart and see if it really holds up. So the problem with PFAS is, along with their really useful properties, like they're really stable, chemically inert, they're really persistent. They are called forever molecules for a reason. I first worked on these early in the days of PFAS research in the year 2000. I'm now back working on them because the problem has just gotten worse. They are also bioaccumulative, so they get into organisms and they bioaccumulate up the food webs. Humans, especially if you eat meat or dairy products, eat at the top of food webs, so that puts us in a particular risk. They are toxic, many modes of toxicity demonstrated, including that they interfere with our hormone systems and thus affect reproduction and impair our fertility, and they're everywhere. So you can measure them in the blood of almost every human that you test, and they're all over the environment. The EPA just last year issued very low advisory health limits for allowed levels of these forever chemicals in water, as low as 4 parts per quadrillion, which is basically way below your detection limit. So if you detect any PFAS in your water, you know you have a problem. This now puts huge pressure on water treatment authorities. They now have to remove PFAS, and because they're so stable, we don't have very good scalable technologies to do that. So returning to the energy side of synthetic chemicals and PFAS, I want to examine this common statement that we need chemicals like PFAS in order to promote the transition to clean energy technology. And so you can see several news articles or editorials that have been published recently that are basically all saying, so the European Union is aggressively starting to regulate problematic chemicals such as PFAS, and basically the chemicals industry is saying, well, if you do that, we won't be able to achieve decarbonization. I want to stop on one example here. Lithium-ion batteries is an especially problematic common use of the forever chemicals. So as we transition and electrify transportation, we really need to avoid using chemicals like PFAS. I was just at the American Chemical Society meeting earlier this week, and I was catching up with my colleagues Jennifer Guelfo and Lee Ferguson, and they pointed out a paper they have under review for Nature Communications, where they did toxicity analysis of this particular PFAS molecule commonly used in lithium-ion batteries and identified that it is actually quite toxic. This was not previously known, and so they are trying to get the word out so that we can stop using this problematic chemical. And so what we need to do is apply the essential use concept and evaluate for various use cases of PFAS, for example. Is it really essential? Is it non-essential? And are there substitutes available, or could substitutes be developed? And what you find is that in most cases, the essential use is actually not there. They are non-essential, or you can substitute them. So the good news is that many companies have already demonstrated that you can develop PFAS-free materials for clean energy technology. Lithium-ion batteries, electrolytes for batteries, ion exchange membranes for fuel cells, solar panels, and semiconductors. And this information comes from a former student of mine, Dr. Lydia Yall. She now works at the Green Science Policy Institute, which works at the Science Policy Interface to inform policies around harmful and non-sustainable chemicals. And when she analyzed these companies that have demonstrated that they can develop PFAS-free energy technologies, some themes emerged. Some of them made materials and technologies that were PFAS-free accidentally. It wasn't their objective. Often, because PFAS are specialty chemicals, they're very expensive. Removing PFAS can dramatically reduce your costs. Sometimes PFAS isn't actually the best material for that particular application. And many of these companies would welcome regulation, restrictions on PFAS. Many large manufacturers are also working on PFAS-free technologies, but they aren't publicly disclosing this at the time. And then here are two examples. If you avoid using PFAS for battery electrodes, you also avoid having to use a quite harmful solvent, so you get a co-benefit there, and it also reduces your costs. Solar panels made without a PFAS backing material are just 1% more expensive than the common versions with PFAS. So if I started to convince you that this is an important opportunity, an issue to consider, then what we need to focus on is the source of PFAS. We need to stop manufacturing so much PFAS and putting it into use. We are not going to get anywhere if we try to remove it once it gets into the environment. So we really need to focus on the start of the supply chain and avoid baking PFAS into our clean energy technology transition. So decarbonization focuses on the problem with carbon dioxide, but it shares a similar problem with PFAS, although they're very different molecules, which is that they are forever molecules. They have very long environmental lifetimes, which allows them to have their deleterious effects on the planet for long periods of time. I wanted to end just by talking about some expertise in PFAS research here at CMU. So my colleague in chemistry, Carrie McDonough, she focuses on understanding how are we exposed, humans exposed to PFAS, and especially focuses on considering non-PFAS precursors that get transformed into PFAS. So we need to widen the lens and consider chemicals that are precursors and become PFAS and then get into humans. I focus on the atmospheric side of PFAS. A lot of PFAS is vented directly into the atmosphere from the manufacturing facilities. There's no regulations on that. They transform, they get washed out of the atmosphere, they enter our water resources and our food webs. I also work on technologies to destroy these really persistent molecules, and more recently I've started to work in the policy space to inform policies around harmful chemicals. And then finally, we are about to open an automated science lab about a mile from here in Bakery Square. It's called the CMU Cloud Lab. And this is full of instruments that can do the important chemical analysis so that we can certify and assess if materials are or are not PFAS-free. There is very poor transparency in our chemical supply chain, so even companies or researchers that want to avoid problematic chemicals such as PFAS don't always know what they are buying, and so people can come, we can work with industry or academics, use the Cloud Lab to do this analysis to determine is there PFAS or other harmful chemicals in the materials that you're considering for your particular technology application. Thanks so much for having me.